Hello everyone. In this video, we'll discuss about adjoint of a matrix and a method for finding inverse of a matrix using adjoint of a matrix. The adjoint of a square matrix A of order n, that is A equal to Aij of n by n, is defined as the transpose of the matrix capital Aij of order n. If since A is of order n, its transpose is also of a square matrix of order n. Now what is Aij? Capital Aij is the cofactor of the particular element Aij. So you have to find cofactor of each of the element Aij. After finding cofactor of the elements Aij, write it as a matrix, then take the transpose of the cofactor matrix. That will be the adjoint of a matrix. For example, you consider a 3 by 3 matrix. Let A equal to A11, A12, A13, A21, A22, A23, A31, A32, A33. So adjoint of A, that is the matrix adjoint of A, will be the transpose of A11. Here capital A11 is the cofactor of small a11. Capital A12 is the cofactor of small a12, and so on for other elements also. Now the transpose of this matrix, that is cofactor matrix, that will be the adjoint of A. So here adjoint of this matrix A is this matrix, that is A equals to adjoint of A equals to A11, A21, A31, A12, A22, A32, A13, A23, A33. So that is the transpose of the cofactor matrix. Now let us do some examples. If A equals to 1, 2, 3, 4, we will find the adjoint of A. So here the first we have to find the cofactors of each of the element. So A11, that is 1. Cofactor of 1 is delete first row, first column. So the 4 is there. Since 1 plus 1 is even, it will remain as 4. That is in this case cofactor equal to minor. Now A12, so you delete first row and second column, so it will be 3, but it is 1 plus 2 is odd number, so cofactor will become minus 3. Similarly, A21 will become minus 2. Delete second row, first column, 2 will come A21. That is the 2 is the minor. So a minus 2 will be the cofactor. And for A22 it will be 1. The cofactor by deleting second row, second column. So that means cofactor matrix, cofactor of each of the elements will be 4, minus 3, minus 2, 1. Now adjoint of this will be transpose of the cofactor matrix. So that means it will be 4, minus 2, minus 3, 1. So this is the adjoint of the given matrix. That is adjoint of matrix 1, 2, 3, 4 is 4, minus 2, minus 3, 1. To get the adjoint of a 2 by 2 matrix, you just have to interchange the diagonal elements. These are the diagonal elements. To get the adjoint of this, interchange these two elements, that is interchange the position of the diagonal elements and change the sign of the non-diagonal elements. For non-diagonal elements, change the sign without changing their position. So directly you will get the adjoint of a 2 by 2 matrix, that is by interchanging diagonal elements and changing the sign of the non-diagonal elements. Now we will do an example for finding adjoint of a 3 by 3 matrix. So let A equals to 1, 3, 3, sorry. A equals to 1, 3, 3, 1, 4, 3, 1, 3, 4. So now you have to find cofactors of each of the elements. So for first element, that is 1, delete first row, first column. So that is 16 minus 9, so cofactor will be 7. Then A12, it is delete first row, second column, so it is 4 minus 3 plus 1, but it is A12, so cofactor will become minus 1, and so on. So now adjoint of A will be the transpose of the cofactor matrix. That means it will come as 7 minus 3 minus 3. So it will be cofactors of A11, A21, A31 in first row. So that is 7 minus 3 minus 3. And in second row, cofactors of A12, A22, A32. So that is minus 1, 1, 0. And in third row, it is cofactors of A13, A23, A33. So this will be minus 1, 0, 1. So the adjoint of A is here 7 minus 3 minus 3 minus 1 1 0 minus 1 0 1. Here first column is cofactors of first row elements. Second column is cofactors of second row elements, and third column is the cofactors of third row elements. Now we'll go to a theorem regarding adjoint of a matrix. So let A be any given square matrix of order n. A be any given square matrix of order n. Then A into adjoint of A, that is product of the matrix and its adjoint, that is A into adjoint of A, equal to adjoint of A into A is equal to determinant of A into I, where I is the identity matrix of order n. I is the identity matrix of order n. So if you multiply a matrix with its adjoint, you will always get this one, that is determinant of A into identity matrix, where I is the identity matrix of the same order as the given matrix. So let us verify this theorem. So you consider a 3 by 3 matrix. A equals to A11, A12, A13, A21, A22, A23, A31, A32, A33. Its adjoint is A11, A21, A31, A12, A22, A32, A13, A23, A33. These are the transpose of this matrix is the transpose of the cofactor matrix. Now if you multiply these two, what we are going to get, let us see. If you multiply the first row and first column, that is first element of the product, the first element of the product will be A11 into A11, A11 into A11 plus A12 into A12 plus A13 into A13, that is first row, first column. Now from the property of the cofactors, if you multiply any row with the corresponding cofactors, then take their sum, it will be always equal to determinant of A. So sum of product of elements of a row with corresponding cofactors, that means we are multiplying with the corresponding cofactor, then you will get determinant of A. And if we are multiplying with other cofactors of other row, then it will be 0. So here first row, first column, when you multiply, it is elements of first row with their cofactors, so it will become determinant of A. Then first row, second column, so that is first row into cofactors of second row, so that will become 0. So here only the diagonal elements in the product, only the diagonal elements will be determinant of A, all others will be 0. If you take this particular element, this is obtained by multiplying second row, second column. So second row, second column means it is second row elements with cofactors of that particular row, that is cofactors of second row. And the other elements in that particular row is equal to 0, because these are second row multiplied with cofactors of first row and third row respectively. So that means we will get determinant of A 0 0 0, determinant of A 0 0 0, determinant of A. So determinant of A is common in this matrix, so it can be taken outside. So it will be determinant of A into identity matrix. So since we took this as a 3 by 3 matrix, I is also of order 3 by 3 here. So this is a 3 by A, determinant of A into I, where I is a 3 by 3 matrix, because we took a 3 by 3 matrix here. Now similarly, if we do the reverse order, adjoint of A into determinant of A, in that case also you'll get determinant of A equal determinant of A into I. So the result is A into adjoint of A equal to adjoint of A into A equal to determinant of A into I. If you multiply a matrix with its adjoint, you will always get determinant of A into identity matrix. Now we can define two types of matrices using their determinant. These are singular matrix and non-singular matrix. A square matrix A is said to be singular if determinant of A equal to 0. If determinant of A equal to 0, then it is a singular matrix. For example, if A equals to matrix 1, 2, 4, 8, here we can see that the determinant is 0. So this is a singular matrix. And if determinant of A not equal to 0, then it is said to be a non-singular matrix. If determinant of A not equal to 0, then it is said to be a non-singular matrix. For example, matrix 1, 2, 3, 8 is a non-singular matrix because if you find the determinant here, it is 2. Determinant is 2, which is not equal to 0. So this is a non-singular matrix. Now in first theorem we have seen that A into adjoint of A equal to determinant of A into identity. So A into adjoint of A equal to determinant of A into identity. Now if you take determinants on both sides of this, so this will become determinant of A into adjoint of A equal to determinant of this matrix. Determinant of A into I means determinant of A 0, 0, 0, determinant of A 0, 0, 0, determinant of A. So that means determinant of A is common in each of the rows here. So you can take out determinant of A common from each of the rows. So it will become determinant of A cube. Then determinant of the identity matrix, this is 1. So this is equal to determinant of A cube. Now the left hand side, determinant of A into adjoint of A, this can be written as determinant of A into determinant of adjoint of A, because determinant of AB equal to determinant of A into determinant of B. So that means determinant of A into determinant of adjoint of A equal to determinant of A cube. So suppose A is a non-singular matrix, we can divide both sides with determinant of A. Suppose A is a non-singular matrix, we can divide both sides with determinant of A. So in that case, we will get determinant of adjoint of A equal to determinant of A square. Determinant of adjoint of A equal to determinant of A square. This is because we took a 3 by 3 matrix. A and A is a 3 by 3 matrix. So this result in general we can say that if A is a non-singular matrix, A is a non-singular matrix, that means determinant of A not equal to 0 of order n, then determinant of adjoint of A, that is determinant of adjoint of A, will be determinant of A to the power n minus 1. Determinant of A to the power n minus 1. This is if A is a non-singular matrix, that is if determinant of A not equal to 0. Now next we will move to an important theorem. So this theorem is the necessary and sufficient condition for a square matrix to possess an inverse. So that is, a square matrix A is invertible. A square matrix has an inverse if and only if it is non-singular. So that means if its determinant is not equal to 0. So a square matrix is invertible if and only if determinant of A not equal to 0. So this is an if and only if condition. So that means both ways this is true. So if A is invertible, then determinant of A not equal to 0. Or in other words, if determinant of A not equal to 0, then A is invertible. That is both ways this is correct. So that is why it is written as an if and only if condition. So let us prove this one. So first we will assume that A is invertible. We will prove in the direct way, that is AB invertible matrix. So then we have to prove that A is non-singular. Now since A is an invertible matrix, then there exists a matrix B, square matrix B of the same order, such that AB equal to BA equal to identity. So this is from the definition of inverse of a matrix. Now if you take determinant on both sides, if AB equal to I, from in that if you take determinant on both sides, so it will become determinant of AB equal to determinant of I. So determinant of AB equal to determinant of A into determinant of B, and determinant of I equal to 1. So determinant of A into determinant of B equal to 1. So the product of the determinants equal to 1. So both of them should be non-zero. So this means that determinant of A should not be 0. So determinant of A not equal to 0. So hence A is a non-singular matrix. So A is non-singular. So we assume that A is invertible and we got that A is non-singular. Now conversely, we will assume A is non-singular, then we have to prove that A is invertible. So A is non-singular means determinant of A not equal to 0. And from theorem 1, A into adjoint of A equal to adjoint of A into A equal to determinant of A into I. A into adjoint of A equal to adjoint of A into A equal to determinant of A into I. Since determinant of A not equal to 0, we can divide this throughout with determinant of A. So once you divide this with determinant of A, we'll get A 1 by determinant of A adjoint of A, then 1 by determinant of A adjoint of A into A equal to I. So suppose if you take B equal to 1 by determinant of A into adjoint of A, 1 by determinant of A into adjoint of A as B, then this is same as AB equal to BA equal to identity. So AB into BA equal to identity, where B is 1 by determinant of A into adjoint of A. So if determinant of A not equal to 0, so we got a matrix B which is equal to 1 by determinant of A into adjoint of A, such that AB equal to BA equal to identity. So now using the definition of inverse of a matrix, we can say that A is invertible because AB equal to BA equal to, we got identity. Since determinant of A not equal to 0, this is well defined. 1 by determinant of A into adjoint of A is well defined. So thus we can say that A is invertible, and here A inverse equal to 1 by determinant of A into adjoint of A. So this gives us another way of finding A inverse, that is using A inverse equal to 1 by determinant of A into adjoint of A. So this is possible only if determinant of A not equal to 0. So that is the necessary and sufficient condition for the existence of inverse of a matrix. Inverse of a matrix exists only if determinant of A not equal to 0. Determinant of A equal to 0 means inverse does not exist. That's all in this video. We'll do some problems based on this in the next video.